Okay, so we'll begin by reviewing a few algebra concepts which you must have seen. A zero divisor in a ring R is element A such that there exists some element B. Okay, so some part didn't get copied here. Some element B which is non-zero in R, such that A times B is 0, and A is said to be nilpotent if some power of A is 0. Yeah. So 0 qualifies as both nilpotent and zero divisor. Okay, so we'll take some people take the convention that 0 is is not a zero divisor or not nilpotent, but we will assume they are. Okay, so that way both conventions are prevalent. Let R be a ring is said to be reduced if it doesn't contain any non-zero nilpotents, and a ring is said to be an integral domain if it doesn't have any non-zero zero divisors. Okay, so these things you must have seen. So I'll just run through them. Yeah. So have you seen Jacobson radical? The definition of Jacobson radical?
Yeah.
Yes, we have seen. Yeah.
Yeah. So it's just the intersection of all maximal ideals of R. By definition, it's an ideal because it's intersection of all of ideals. And nil radical also you must have seen is the set of, you look at the set of nilpotents and that forms the nil radical of R. Yeah. And this is also an ideal. Why is this an ideal? So one way is to just check that intersection of so one way is to directly check that is closed under multiplication and addition and multiplication from the ring. And there is also one result which says that nil radical is same as the intersection of all prime ideals of R. Yeah, so I hope you have seen these results as well. And so nil radical has a description like Jacobson radical in terms of intersection of ideals. And so you must have seen, so also Jacobson radical has an element-wise description like for the nil radical here. So you take x in R such that 1 plus xy is a unit for all y in R. Then you get that x, this set is also same as the Jacobson radical. So have you seen this star?
Yeah.
Yeah. So this, I hope these things were covered. Yeah. So these are not difficult statements. It's just 1 or 2 line proof. And of course, no matter which description you want to take, you can always see that nil radical is contained in the Jacobson radical. Yeah? Because maximal ideals are prime ideals. So it is Jacobson radical is a small intersection over a smaller collection, and nil radical is a intersection over a bigger collection of sets. Yeah, so the intersection is going to be smaller. Yeah. And so sometimes they may be equal, but sometimes they're not. Yeah. So can you give an example when they are equal, Jacobson and nil radical? Some example of a ring for which Jacobson and nil radical are same.
Yeah, obviously Z will work. Yeah.
Z, yeah. So for instance, Z will work because you take the intersection of all prime ideals, then you get 0. Yeah. And so nil radical is same as the Jacobson radical. Also you can check that even polynomial ring in as many variables as you like, but let's just take one variable. These are examples where Jac R equals nil R. Or you can take quotients of them as well.
Any finite commutative ring maybe. Yeah, right.
any finite commutative ring is okay. Yeah.
Yeah.
But polynomial rings are infinite, but still it's okay.
Over actually any ring will work. I mean, not just field.
Oh, that's what you're saying, yeah?
Yeah, over
Is,
any ring. Yeah.
Over any finite commutative ring, not over any ring. This is
No, over any ring. I mean, if you take any ring A and AT will satisfy Jacobson equal to nil radical.
I am not so sure. If I take over a local ring, are you sure?
Yeah, I think so.
So over finitely generated ring, I think it's okay, but I'm not sure about anything. So I'll have to check, yeah? So, CPX. Yeah, so I'll have to check. I'm not so sure.
Yeah, okay, I'll check it as well.
I don't think this is true. Yeah, so because so maybe all the maximal ideal contains the maximal ideal of the ring you studied. So one has to. I'm not so sure it works for any ring. Yeah, but
okay, I'll check it.
But what you can do is take any. So this is maybe this theorem we will see that you take a finitely generated a ring. Finitely generated ring over integers or over field, then Jacobson and nil radical are seen. So this is a consequence of what is called Hilbert-null disturbances. Yeah. So anyway, but we'll see that later. So what's and then of course since we already discussed this, if you take a local ring, so you know what a local ring is? A ring with only one maximal ideal. Yeah, so you take a non-trivial local ring, not like finite rings or something. So you take a local ring, for instance, K power series T. This is a local ring with only one maximal ideal, or you can take Z localized at some prime P. I don't know if have you seen localization? Was that covered in?
Not, yeah, we have seen it, but not in detail.
So it wasn't covered in Algebra 3 localization.
It's not part of the syllabus, but we have seen it.
It was so. Was it covered in Algebra 3? I don't want
to.
Okay.
It was taught. Yeah. It was taught.
So maybe I'll cover a bit of it. So this is. So if you like, so I don't know if this was the notation, but you consider this, then S inverse Z. This is also denoted by Z localized at P. So this is also a local ring, meaning there is only one maximal ideal. So these kind of rings have no hope of being, no hope of having this property that Jacobson is same as nil radical. Okay, because Jacobson radical is basically the maximal ideal, and nil radical, I mean, these are integral domains, so nil radical is trivial. Yeah, not just reduced, but the okay, makes sense so far? And then, so the reason I'm doing this is the main objective is to study radical of an ideal. Yeah. So rad I for R ideal I is called the radical of an ideal I, and it's also denoted by the square root I. And so the elements of this is F such that some power of F is in I. Okay. And so have you seen radical I as well in Algebra 3?
Yeah, we have.
Was this defined in Algebra 3?
Yes.
Yes, okay. So it is not different from, it's not too far away from nil radical actually, because yeah, so another description of rad I is in terms of nil radical, what you do is you have a natural quotient map, yeah, from R to R mod I. So rad I is phi inverse of nil radical of R mod I. Okay. So that's more or less the definition. So so if they exist, so I mean, if you consider an element of rad I from the definition, that is f such that some power of f is in I, that tells you that f bar, its image under phi, is a nilpotent guy, because some power of it is going to belong to I. So it belongs. So that tells you that if f belongs to rad I, then it belongs to phi inverse of nil radical of I. And conversely, if f belongs to phi inverse of nil radical of I, that means some the image of f under phi, so phi f, some power of phi f is 0 in R mod I, which means some power of f is in I. Yeah, so this is another way of thinking about it. And if you think in these terms, then the second description follows from the fact that nil radical of I is intersection of all prime ideals in that ring. Yeah, so and use the fact that ideals, or ideals in general of R mod I is in one-to-one bijection with ideals of R containing I, and this bijection preserves maximal ideals and prime ideals and so on. Okay, so prime ideals.
Can I say something?
Yes.
Okay, so what I want to say was that in any polynomial ring, it is true that if you have a polynomial, then it's nilpotent if all the coefficients are nilpotent, right?
Yeah, that's right.
Yeah, but then if you multiply it by any polynomial and add 1, then it's going to be unit, because it's unit if the first coefficient is unit and the rest of them are nilpotent.
Nilpotent plus a unit is a unit. Unit.
Yeah. So therefore, it belongs to the Jacobson radical of R2.
Yes.
So for any polynomial ring, nil radical is Jacobson radical, right? That proves it.
Okay, 1 second. So
I mean, if polynomial is nilpotent if and only if all the coefficient is nilpotent, is that true for non-commutative ring also?
No, I mean commutative unital ring. Commutative unital.
Here we are always assuming the ring is commutative.
Yeah.
So we are not really.
Yeah, then it's fine. For any commutative ring, it's Jacobson radical is same as nil radical.
So if you are saying that if I take some element in the Jacobson radical, that means 1 plus xy is a unit for all y in R.
And so in particular, 1 plus x is unit.
In particular, 1 plus x is unit. So
all the coefficients in x must be
1 plus x is unit. Then how do you get that x is nilpotent?
Because x is some polynomial, right? And 1 plus x is it's a unit plus. I mean, the coefficients of 1 plus x are the same as x except the last coefficient, which is a unit.
So okay, so you are starting with something in the Jacobson radical. You are trying to show that it's in nil radical. Yeah.
Yes.
So you start with some polynomial f, such that call it x itself. Yeah. So start with fx, some polynomial fx, and with coefficients in R, and suppose that 1 plus fx is so fx is in the Jacobson radical. Then what does it mean? So 1 plus fx is a unit. But how do you get that fx must be nilpotent?
Because if a polynomial is unit, then all the coefficients except the last coefficients are nilpotent. So all the coefficients of fx must be nilpotent.
If a polynomial is unit, all the coefficient except for the constant term must be
nilpotent.
Nilpotent, right? Yeah. Otherwise, you can't get to 1. So
all the coefficients of f are nilpotent. So if
yes. So F must be nilpotent. Yeah, that's right. Yeah, so that so I guess polynomial ring over any ring is yeah, so it should be just finitely generated. Yeah, that's it. So polynomial ring over any ring is has this property. Okay. So now radical of yeah. So let's get to so this radical of I is uh, uh, is this guy. So we will see it has some close property with. I mean, geometrically, it's sort of very close to I. So we'll define zero sets and stuff, and there is not much difference between zero set of I and zero set of radical of I. Because if F vanishes, F power n vanishes. So in that sense. Yeah. So some observation, I is always contained in the radical of I. If I is contained in J, then radical of I is contained in radical of J. And radical of I is equal to radical of any power of I. So these are some obvious directions. We see that I is called a radical ideal if I equals the radical of I. So that I itself is radical. You don't get anything in the idea. If you take radical, you don't get anything bigger. And I is a radical ideal if and only if R mod I is what
reduced, right?
Reduced, yeah?
Reduced.
Yeah. R mod I is reduced. Is this clear? So the point is rad I equals I implies is equivalent to saying that phi inverse of so yeah, so that it implies that phi inverse of nil radical of R mod I, which is that I, is equal to, well, phi is this, maybe I should have called it Q, but anyway, phi is this map R to R mod I is equal to I, but I mean, there is a bijection between ideals of R and ideals of R containing I, and so so this that tells you that this nil radical must be same as zero. Yeah, so this implies also so I so nil R mod I is the zero ideal, since phi inverse of 0 is also I. Okay. So any questions so far? So I hope this is not too fast, because I mean it was a review, so you have seen on this. Okay, so now we'll talk about affine space and the zero set. So since you said you have seen Zariski topology, you may have seen these as well, but nevertheless, we'll go at, since this was anyway outside the syllabus, we'll go at our own pace. Okay, so definition. So first we'll define affine space and then zero sets and so on. So let K be an algebraically closed field. So many of the definition, etc., doesn't really need algebraically closed field, but some of the results we want to prove we'll need it. And anyway, when people talk about varieties, they invariably assume that the base field, at least these days, assume that the base field is the field is algebraically closed. So K be an algebraically closed field. So for example, you can take K to be C, Q bar. So Galois theory is done. So I am assuming you know what Q bar means, yeah? And so algebraic closure of Q, FP bar, and so on. Okay, you can take algebraic closure of whatever your favorite field is. And this set of n tuples of K, so maybe Kn, if you like, is called the affine n space over K. Over K, yeah, and it's not denoted by K power n, and it is denoted by An or Ank. To be more precise, if you want to say over which field it is, you know, sometimes simply by An. So K power n usually is reserved for vector spaces so one somehow thinks of it as there is some addition or multiplication you can do over scalar multiplication or something you can do. But affine n space, we should think of it as points. You can't do any other operation on them. Yeah. So some geometric object, not some algebraic object. Okay. So this is what affine n space is, and so for each n greater equal 1, you get some affine n space. And then you have some subsets of which we want to call algebraic sets. So these will help us give a topology as well, and these are the more interesting objects. These are the interesting objects we want to look at. So like last time we talked about, it's a zero set of x squared plus y squared equals 1. So that's a circle. So these are the geometric objects we want to study. Yeah. So definition. Subset X of A and K is called is called an affine algebra. Affine. Okay. So this is freezing. Sorry, so the software somehow crashed. Let me try one more time. Okay. It's called an affine algebraic set set if X is the zero set of a subset, zero set of a collection of polynomials. Yeah. Of a collection S of polynomials in K. So you want zero set, it should be a subset of A and K. So you need n variables. So it should be a polynomial heading in n variables. Okay, so that's the definition of a fine algebraic set. Okay, and this X is denoted by Z of S, algebraic set. So, so first observation is that so you don't have to look at, one shouldn't look at, or one need not look at arbitrary subsets of this arbitrary collection of polynomials in Kx1 to Xn. So Z of some S is same as Z of the ideal generated by S. Yeah. So the ideals, that's why the ideals are important. Okay. And again, this has frozen. Okay, so and this proof is the proofs initially are all straightforward. Yeah. So so for instance, if maybe I should have done one example. Okay, so after this proposition, we'll do one example. So or you can think of S to be, you know, x squared plus y squared minus 1. So one example we have seen, maybe we'll do some more non-trivial, more than one polynomial example after this. Yeah. So if so let X belong, so or maybe some point P belongs to ZS. So P is some n tuple, yeah, in A and K, and it belongs to ZS implies, so this happens if and only if P is the zero set of every polynomial in S. Yeah, so this happens if and only if FP is 0, P in A and K. Yeah. ZS if and only FP is 0 for all F in S. Yeah. But if FP is 0 for all F in S, then FP is also, so then GP is also 0 if G is summation AI Fi, I equals 1 to M, and Fi's are in S and AI's are in the polynomial ring Kx1 to Xn. Because of course, if the later statement holds, the so GP is 0 for all G like this, then of course GP is 0 for then of course FP is 0 for all F in S, because you know you can take all the other AIs to be 0, one of them to be 1, and that F. Yeah. But the other way is also true, because you know, linear combination of zeros are 0, yeah? which is same as saying that, but this is precisely the ideal generated by S. Yeah? So GP 0. So maybe I should write for all G of this form. So for all G in the ideal generated by this. Okay. So this is this proposition. So let's see some example. So maybe since I want to involve more than one polynomials, so let's look at A3, yeah, 3 space, and let's take S to be, for instance, x squared plus y squared. Yeah, so x, y, z are the coordinates. Yeah, so instead of x1, x2, x3, I'll just do this equals 1 or minus 1. And maybe, I don't know, something else. So z equals 2. Yeah. So if z minus 2, so this is same as saying z equals, so we are setting it to 0. Yeah. So then what is zs? So this is, and this is maybe a, b, c, such that a square plus b square in C3, let's say, such that a square plus b square equals 1 and c equals 2. Yeah, so you know what it will look like. It's so if it was so if you pretend instead of c you take the real picture, so maybe so it, I mean, as I said, the definition works in any field, but just to picture it, and this if you look at the 0 set of this thing, it's this guy, yeah, x, y, and z, and yeah, so this is annoying now. Yeah. X, Y, Z, and there is a circle at height 2. Yeah, so this is the 0 set. Okay, if you take the 0 set of only one guy, then it's the cylinder. If you take the 0 set of the other guy, it's the plane at z equals 2. And hence, this is the 0 set. This is the intersection of these two. Okay. So this is what you get. So this also tells us some other things. So maybe the so maybe we'll make these observations. So maybe time to go to next page. Okay, so some observations about these operations. So first, if I is contained in J, so I mean we can look at just ideals instead of because the 0 set doesn't change. Yeah, ideals in K x1 to xn. And then what can we say? Then if you look at Zi, So if it's this smaller ideal, then the zero set is going to be bigger. Yeah, like in this example, if I consider the ideal generated by just one of the equation, the zero set is bigger. Yeah, it has to satisfy less conditions, less number of conditions. So Zi is bigger than Zz, and okay, so I've written, so there is an inverse operation too, which I forgot to write. So given a set, a collection of polynomials, you can write, make a zero set out of it. Similarly, given a subset of A and K, or or given an algebraic subset of, so even a, 1 second. So given algebraic subsets of A and K, so let's say X and X, so maybe this is definition. X B and algebraic subset of Z of A and K. Okay, then define Ix to be f in kx1 to xn, the polynomial ring in n variables, such that f vanishes at each of the points of so f a1 to an is 0 for all a1 to an in X. Okay. So I guess to define this, you need not even assume it's an algebraic set. Yeah. So you can drop this assumption. So for any subset, you can define this, and it will always be an ideal. Then Ix is an ideal in kx1 to xn. Yeah. So if you think in these terms, I mean, it's natural to look at ideals. Yeah? So this is how I'm pretty sure people have thought about why ideals are important and so on. Yeah? So the geometry already existed and algebra came later. So, and this is called the defining ideal of X. Okay. So somehow when I'm writing and there's a Zoom talk going on, the writing becomes, so it freezes. So maybe next time onwards, I'll try to write down in advance more or less everything, and then present it. So it may seem like it's going fast, but if I'm going too fast, then you can stop me. So then there won't be any technical issues. Okay, so now so there is an analog of this thing. So so if X contained in Y, a fine algebraic set sets in A and K. Then A and K, then Ix, ideal, defining ideal of X is going to be bigger, yeah, because X is smaller than defining ideal of Y. Okay, and so as I said, if you take, for instance, Z of I is same as Z of radical of I. I'm just denote this card. That's the notation I usually use. That's another observation to look at. And what else do I want to say? So there's a, I mean, these are sort of inverses. These operations are sort of inverses, but that's a more difficult result, yeah? So maybe I'll put it as a proposition without complete proof. So I of, so defining ideal of zero set of some ideal. So this, since this I and that I look same, I'll put a different name for this ideal J, yeah? Is same as a radical of J for any ideal J in Kx1 to Xn. Okay, so one inclusion is easy. So maybe we'll see which inclusion is easy, and the other one is so I mean, once you keep doing this, both seem fairly reasonable, but the other one inclusion uses Hilbert-Nussbaum, which is a slightly difficult result. So we will see that in this course. Yeah. So let's see which one is easy. So maybe this direction is easy. So let F belongs to radical of J. This implies F power n belongs to J. F power m maybe for some m. So so if F power m belongs to J, that this implies that now F power n, so you are looking at ZZ first, yeah. So so since F power m vanished, so F power m A1 to AN van is 0 for all A1 to AN in ZZ. Yeah, because F power m belongs to J, then of course these are collection of points on which every elements of J vanish. So this will happen, and this implies that F A1 to AM is equal to 0 for all A1 to AN in ZZ. Yeah, because you know, we are in a field. I mean, this is an element of a field K, which is a reduced string. So some power is 0. That means it must be 0. So this tells us that F belongs to ideal of definition of Z. So we see that radical of J is indeed contained in the in I of Z of Z. The other inclusion, as I said, is a bit difficult. So this is Hilbert-Nuss's answer, which we'll see next, later. Yeah. Okay. But so we will see a variant of these constructions. So we'll see instead of working with affine n space, we will change our space as a spectrum of a ring, so set of all prime ideals. And then we can define again zero set and ideal of definition. And then this statement, with those definition, this becomes a triviality. Yeah? So this statement becomes is more or less tautology. Yeah, but for algebraically closed, but if you're working with points in a affine n space over an algebraically closed field, then you have to work with this. So this result, for instance, requires K is algebraically closed. Otherwise, you'll have to work with maximal ideals. Okay. So yeah, so now maybe how these things behave with respect to okay, there are some questions. Is I the ideal generated by S? No. Oh, sorry. Okay, so where was this? So is it clear, Aitro, at the moment?
Yes, sir, it's clear.
Okay. So let me just list down some more properties of these things. Okay, so if you look at Z, not integers, but the zero set of sum of two ideals, I plus J. So this is the ideal generated by I and J in Kx1 to Xn. So everything is in this ring, Kx1 to Xn. So what can you say about this? This is, so in fact, this is same as zero set of I union J. Yeah, and this is same as zero set of I intersection zero set of J. Okay, so this is how it behaves. You know? Similarly, because it has to run. I mean, those elements which. So these are just tautology. Yeah. So this is set of elements, set of points, which vanish for every polynomial in I plus ideal generated by I and J. But we know that that is same as every polynomial which vanish at for polynomials in I and points which vanish at every polynomial contained in J, which is same as points which vanish for every. So this to this is sort of tautology, and this to this is what we discussed earlier. Yeah. Okay. And then so this Zi equals Zi I already talked about. So so apparently I'd written some proof of it earlier, but okay, so maybe I should prove something. Oh, there is one statement missing. So Zi intersection J is Zi union Zj, and this happens to be same as Zij. Okay, so maybe some parts I should prove. So maybe what I'll do is I'll prove the last one, and the others are similar. Yeah. So 1 and 2. So these two, the first two statement that this is inclusion reversing is obvious. So I won't worry about it. And so 1, 2, 3. So 1, 2, 3 are obvious, and 4 and 5 are, and the proofs are sort of similar. So let me just do the fifth one. Okay. So proof. Okay. So let P belong to ZIC, IJ. This means that so what is IJ? IJ is basically sums of the form FIGI, where FIs are in I and GIs are in J. Yeah. So so this is same as Z of okay, I don't want to write it that way, so let's just yeah. Okay, so let's try to do all inclusions. Yeah, so P belongs to Z I intersection J. So I mean somehow I don't see the proof written down very carefully here. So so that means that f of P is 0 for all f in I intersection J. Yeah, so so this implies that P belongs to, so so then since f of P vanishes for all f in I intersection J, so of course P belongs to Zi. Yeah. And so okay, yeah, maybe I didn't think so. Maybe use these earlier properties. Yeah. So I intersection J is contained in I. So this tells us that Zi is contains Z I intersection J. So this implies that sorry, Zi is contained in Zi intersection J, which implies that and similarly Zj, so Zi union Zj is contained in Zi intersection J. Yeah, so this this direction is okay. And now we take something in this guy, and we want to prove that inclusion. So let's say A1 to AN is an element of Z I intersection J. So this is same as saying that FA1 to AN is 0 for all f in I intersection j, which implies for all f in, so it implies that f a1 to an is 0 yeah, so for all f in ij, because ij is since ij is contained in I intersection j, yeah, and this implies so f a1 to an, so f belongs to ij means you can you can write it as yeah, so is equal to 0. So say for so f is g times h and g in I, h in j, then and this is 0 is same as saying g a1 to an is 0, or g times h is 0, which is same as saying g a1 to an is 0, or h a1 to an is 0. So if so if say g, so for some g in for all g in I, or for all h in j, yeah, and note that if for some g in I, g a1 to n is non-zero, for some g in I, g a1 to an is non-zero, then for all h in j, for all h in j, h a1 to an must be 0. Yeah, otherwise you know, we won't get that that product won't vanish. Yeah, so that tells you that this A1 to AN has to belong to Z of I, or A1 to AN has to belong in Z of Z. Yeah, which is same as saying A1 to AN belongs to the union. Unions, let's say. Okay, so I hope, though it took a long time, I hope this is not confusing. Yeah. So in fact, what we showed is that so we didn't really use just the fact. So what we showed is that A1 to AN belongs to Zij, then so what we showed is that A1 to AN belongs to Zij, implies A1 to AN belongs to Zi union Zj. Yeah, and of course, so which means that we showed that belongs to. So what we showed was Zij is contained in Zi union Zj, and Ij being a smaller ideal than I intersection J, its zero set contains Zi intersection J. And we had already seen this inclusion, that this is contained in Zi intersection J. So we have equality all through it. Okay. So this is what we started with here. So let's start. Okay, so that completes the proof of 4. So I'm pretty sure this completes the proof of 5. So I'm pretty sure 4 is sort of simpler than 5. Yeah, so you can try it out. Okay, any questions? So there's some chat. I see. Yeah, but I also so I wanted to write it in many in this way so that there is a part of the board is visible. So unfortunately, this went long and long, but this is for Karthik. Yeah. So let me just pause the recording and then we can discuss.